Thank you for that. All right, sorry about that. So we're talking about magnetic actuation. We are reviewing some topics. So our H field is our magnetic field intensity. It is the driving magnetic influence external to a material. So I'm going to underline this external here. Essentially, it is the thing that we control. It's part of what's called the magnetomotive force, or a portion of the magnetomotive force, which is typically the thing that we, as an engineer, control in a magnetic system. And it is measured in amps per meter. Then we're going to have our B field. So this is our magnetic flux density vector. And this is the induced total magnetic field inside of a material. It is measured in Tesla, where 1 Tesla is a Weber per meter squared, or that's the same thing as a volt second per meter. So we could also think of it, for what it was worth, would be, I believe it's so Henry is a volt second. We'll just leave it as that. I don't have to get into inductance and all of that kind of stuff. I don't want to derive that. Okay. So our magnetic field intensity vector H and our magnetic flux density vector B are related to each other. So B and H are related to each other by the following relationships. So our B field is going to be equal to mu naught times H plus M, where this M is a magnetization vector. I wanted to use a different color.
Dr. Hardman,
Yes,
when you did your equivalence for the Tesla, volt seconds supposed to be over meter squared.
that's correct. Yes. Thank you for that. Yes. Meter squared. Absolutely. Because a Weber is just a volt second. Thank you for that. So our magnetization vector like so. This represents the internal magnetic polarization of a material that is subjected to an external magnetic field. This is not something that we can really actively measure or anything like that. So we usually put this in another form. So that would be mu naught times H plus chi H, where chi is the susceptibility of the material. And another form, and this is the one that you are most likely to see, is going to be mu r times mu naught times H. So mu r is our relative permeability. And this relative permeability varies from material to material. And for better or for worse, in some materials, it is a nonlinear coefficient, right? So for something like air, it is very close to 1, but for a ferromagnetic material, like certain types of steel and things like that, it can have values of several thousand up to tens of thousands, just depending where along what's known the BH curve we're looking at, depending on how much current we're pushing through our coil. And we'll talk about that here in a couple of minutes. Okay. So this is the relative permeability. It is a material related quantity. And then mu naught is a constant. So this is the permeability of free space. And it is equal to 4 pi times 10 to the minus 7 henries per meter, where for those of you that aren't super familiar with the units of inductance, a henry is a volt second per ampere or a Weber per amp. So the reason why it's 4 pi, well, so I'm sure you remember from your field theory classes or whatever, but the speed of a light in a vacuum C is going to be the square root of mu naught times epsilon naught. So if this guy is 4 pi, that's why epsilon naught has that 8.854 thing, because they have to multiply together to be 2.998 times 10 to the negative 8 meters per second. But yeah, so that's why it's exactly 4 pi. It's from that Millikan oil drop experiment, I believe, from forever ago. So they figured out what the permeability, the permittivity was, and then from that they said the other thing is the permeability. So it is literally 4 pi. Okay, so these relative permeability values are important. Okay, so the value of mu r leads to different classification of materials. And this is very, very general. So when mu r is less than 1, this is what's known as a diamagnetic material. And in a diamagnetic material, the induced field is opposite the applied field. So some examples of diamagnetic materials would be the overwhelming majority of organic materials. So wood, water, stone, all of that kind of good stuff, but also things like copper. So there's a metal that is a really good diamagnetic material as well. So it's not always just organic things. When mu r is greater than 1, we have what are called paramagnetic materials. So in these materials, our induced field is in the same direction as the applied field. Sorry, I'm running out of room here. So these are materials that respond weakly to magnets, but don't retain any magnetism after you remove your applied field. And then when we have materials where mu r is much, much greater than 1, so typically we're talking about thousands of times greater than mu naught, these are typically classified as ferromagnetic materials. And the induced field greatly enhances the applied field. So ferromagnetic materials are usually going to be, so the name literally means iron-related materials, but when we think about permanent magnets, those are usually ferromagnetic materials. They're going to exhibit some characteristic magnetization, and then we can impart permanent magnetization through the use of electromagnets, and we'll kind of talk about that here in a moment. So for ferromagnetic materials in particular, the relative permeability is not usually a constant. Instead, there is a nonlinear relationship, which we call hysteresis. Okay? So I'm going to draw a picture. So let's say the BH relationship for ferromagnetic materials usually follows a hysteresis. Goodness, my handwriting is getting shitty, and then I also can't spell. Curve. And our hysteresis curve is going to look something like this. So I'm going to put my flux vector B on the vertical axis. I'm going to put my H vector on the horizontal axis like so. And typically we would see a curve that looks something akin to this. And I'll kind of explain what's going on here in a moment. Sorry, it's looking kind of shitty. So this is a very rough approximation, but we'll talk our way through things really quickly. So there are several different regions in this curve here. So essentially, if we started right here at this origin point, this would be a raw ferromagnetic material. It would not have any net magnetization because all of its magnetic domains would be randomly oriented for the most part. And so we wouldn't see that it really behaved as a magnet. So we couldn't just take a chunk of iron ore and expect it to stick to our metal refrigerator door or anything like that. Okay. So what we would do is we would place that raw material inside the field of an electromagnet, where the strength of the field generated by the electromagnet is proportional to the current. And so that's why H is measured in amps per meters, essentially, okay? So as we crank up the current, we are applying more and more H field to this medium. And so we have this nonlinear path from this point here all the way up to this point over here. Okay. So the section of this curve, which I'm going to label 1, is what we're going to call the initial magnetization curve. Okay. as H increases, the internal magnetic domains tend to align with the external field until saturation is reached. And saturation is what's going on at that far upper right-hand corner of our curve. So essentially, saturation means that an increase in our H field will not result in a subsequent increase in our B field in our medium. That occurs because we can only make our magnetic domains, like the best we can make them is parallel with the external field. So at a certain point, all of our internal magnetic domains will be parallel with that externally applied field. And if we increase the current, we can't make them any more parallel than they already are. And so we see that our B field saturates to some specific level where changing the current does nothing. So we're going to call this top level here B saturation. Okay. So this is the maximum amount of magnetic flux density that we can see in a given medium. Okay. And it's because, once again, we just can't get any more parallel than parallel. Okay. So as we reduce the current, so as we come back down, we're going to be on this second part of our curve. So that's what's going on from here to here. Okay. So essentially, because we have a ferromagnetic material and it had some, it has magnetic domains, we are going to have a little bit of memory in the form of residual or remnant magnetization. Okay. So section 2 of this curve is the remnant magnetization curve, where the material is behaving like a permanent magnet. So B is non-zero when our current field, or H or I, either way we're looking at it, is zero. Okay. So we have now created effectively a permanent magnet. This residual or remnant magnetization is the reason why up until the last 15 years or so, almost all digital media was stored on magnetic devices, whether that was old school magnetic tapes that were used in cassettes and 8-tracks and stuff like that, or magnetic discs that were used in floppy disks and hard drives and all of that kind of good stuff. It's because we were able to apply a current, set a magnetic state, and then it doesn't go away until we do something to force that magnetic state to go away. So this was a really good way of storing information for a very long time. The overwhelming history of computing has used magnetic media. So this part of the curve here that I'm going to call 3. So now we're in the second quadrant. So what we're doing is we're applying a negative H field or a negative current in order to get rid of that remnant magnetization. Okay. So this is what we're going to call the coercive magnetization curve. And here we are applying a current to remove the remnant magnetization. Remnant REMNANT. Sorry for my shitty penmanship. For section 4 of the curve, so now we're looking at what's going on as we start from 0 on the y-axis and continue going down. This is just us magnetizing the medium in the opposite direction. So if we had aligned all of our magnetic domains to the right, now we're turning them around to make them go towards the left. So it's really the exact same thing that we saw up in our first quadrant. It's just the direction of the current has changed, okay? So if we apply a sufficiently negative H field or apply a sufficiently negative current, we're going to wind up hitting saturation just in the opposite direction, which is what's happening over here. And then this cycle essentially just repeats itself, right? We would have some residual remnant magnetization in the opposite direction as we backed our current or increased our current back towards 0, and then we would have a negative coercive force that's getting rid of that negative magnetization as we head back up. And this cycle just repeats over and over and over again. So the shape of the hysteresis curve, let me put 4 here. So this is just negative magnetization. And I'll just put a note here. B is in the opposite direction of our first curve. Okay. So the shape of this hysteresis curve is also dependent on the material properties. And specifically what I mean is the width of the curve, okay? So if we have a very wide magnetization curve like this, that would be a very, very good thing for digital storage media because it requires a lot of externally applied field in order to get rid of our magnetization or establish our magnetization, right? So we can't accidentally erase data or anything like that very easily. But that would be really, really bad for something like an electrical transformer or an electric motor because we have to dump a lot of energy in to effectively change the state or magnetize the material. Whereas if we want an electrical transformer, we want it to operate very efficiently, meaning we want it to, it's the magnet to be magnetized very easily so that we don't have a lot of losses in that energy conversion process, okay? So wide hysteresis curve, good for data storage, bad for transformers and motors, and then narrow hysteresis curve, good for transformers and motors, bad for data storage. Okay, so now, because we're going to be talking about actuation, let's talk about how we have magnetic fields induce forces, okay? So this is what's called the Lorentz force law, okay? So the force, that was going to be a G, that's wrong. So the force generated by a magnetic field is given by this relationship where our Lorentz force F is going to be Q times vector V crossed into B. This is what is typically used for point charges. And this could be rewritten as I times L crossed into B for current carrying conductors, which is what we're more interested in. So essentially, Q times V, so that is charge times the speed at which the charge is moving, is the same thing as current times the distance over which the charge is moving, okay? So how many of you guys are familiar with the right-hand rule for cross products and all of that kind of stuff? Good, most of you guys, right? So the first thing in the cross product is your index finger. The second thing in the cross product is your middle finger. And then the resultant is your thumb. Great, so this will be real easy to get through then. So let's consider a simple microstructure, right? So this is an optical scanning mirror, okay? So let's say that I have a permanent magnet structure that has been deposited onto a substrate. And I'm going to put another one of these bad boys over here like so. And the field that's generated by this guy is going to be to the left. Okay. So in the middle of a structure like this, a research team developed essentially, it's a mirror that is supported on each side by a torsional beam, okay? So something akin to this. So that's our torsional beam. And then here is our mirror. And on the back side of this mirror, they patterned a coil. And so the coil pattern would look something akin to this. And then I'm just going to jump this guy across all of those. So that's not a point of connection. That's just a 3D structure to where I'm getting my current to flow out. So my direction of current flow is essentially down into the top part of the coil, and then it circulates around over and over through this inductive coil until it pops out the bottom side, right? So if I were looking at a cut line through this device, through the coil structure specifically, I would see something akin to this, right? So 1, 2, 3, 4. So let's just call it 1, 2, 3, 4 conductors on the left, 4 conductors on the right. So the ones, think about me rotating this structure just 90 degrees up off the page. So the ones on the right is going to have current flowing towards me. So I'm going to put a little dot in the middle to represent current flowing towards me. And I'm going to put a little cross over here to represent current flowing away from me as we flip this guy up, right? So the left-hand portion of the coil is going to have current that's flowing, we can think of it in the down direction based on how this is oriented. The right-hand section of the coil is going to have currents flowing in the up direction, etc. Our B field is in this direction. Our current is flowing, so we're going to have some current flowing towards us, so we can literally just use the right-hand rule, right? So current is flowing out of the page. Our B field is directed to the left, and so our force would be in the down direction. So our induced force for these conductors would be down like so. So we would essentially see a force acting into the page on this side of the mirror array. And we would have a force acting in the up direction on this side of the mirror array. And that would then generate a torque on those torsional springs and cause the mirror to deflect either to the left or the right, depending on. So if current is flowing down, we would have a deflection towards the right. If current was flowing up, we would have a deflection towards the left. And we can use this simple optical structure to scan a particular range or field based on how much current we're driving through this guy. So this is a magnetically actuated optical scanner, okay? The magnitude of the torque that is acting on the actuator in this case, so this is our torque, would be current I times our B field times L1 times L2 times N, where L1 is the average length of the coil parallel to the edge of the magnets. And L2 is the average distance between the wires perpendicular to the torsional beam direction. And then lastly, N is just the number of turns in the coil. So this is just one example of how you might use a Lorentz force to be able to generate some kind of rotation in a microstructure. Another structure that we might see would be using, or another way to get actuation with magnetic actuators would be to rely on magnetic attraction and repulsion, right? So we know, yes. Yes. Yes, the average distance between the little sections of the coil. Yes, that's L2. Okay. So in addition to using the Lorentz force to induce torque, we can also use magnetic attraction and repulsion, right? So hopefully most of us, maybe as little kids, tried to, smash two magnets together. And when we had a North Pole facing a South Pole, they came together very easily. But when we had a North Pole facing a North Pole, it was really hard to push them together. Well, we can use that same exact thing on the micro scale as an actuator as well. Okay. So we might have, so let's call, good Lord, that is a terrible looking him. Magnetic repulsion and attraction. No, this is the real part of everything.
Oh,
We're now talking about microstructures, right?
lost me with the computer.
Yeah. So after the Lorentz force law, now we're talking about actual microstructures and stuff like that.
Oh, so the mirror is not the Lorentz?
It is actuated using the Lorentz force law. So Lorentz force law is just something that arises. So that's how torques are generated by magnetic fields. Doesn't matter if you're in the micro scale or the macro scale. I was just reminding you that that existed because it may have been years since you've had your physics class. So that particular type of system utilizes the Lorentz force law in order to generate that micro scale actuation. Yep. And now we are talking about a different thing that can also be used in microstructures to cause magnetic actuation. Okay. So magnetic repulsion and attraction. All right. So this is a complicated-ish looking thing. So I'm going to pre-apologize for this. At some point, I'm just going to have to pay a graduate student to just draw all these things in SolidWorks for me so that I can make, what's it called? PowerPoints. So this is going to look fairly similar from the jump to that optical scanner-ish thing that we just did. I'm going to try to make this as least confusing as possible. So 1, 2, 3, 4.5, 1, 2, 3. All right. So just to be clear here, I've got a torsional spring on here at the top and also at the bottom. But now I'm going to put essentially embedded into this thing yet another torsional spring and a plate. So something akin to this. So that this exterior frame is a gimbal that enables torsional rotation. So we would have something like torsional rotation like this, as well as torsional rotation like this. Okay, so we have two different torsional springs linked together 90 degrees out of phase, and then we've got a plate here in the middle. On the plate in the middle, we then might integrate coils. Again, just simple planar coils. So we might have one over here, and I'll just draw this kind of quick and dirty. So here's one coil. We're not going to worry too much about the electrical connections or anything like that because I'm just trying to talk about what's generally going on with this guy. Here's another terrible looking coil. Coil. And coil. So each of those coils are essentially an electromagnet. They're not essentially an electromagnet. They literally are an electromagnet. So as we pass current through those coils, so if current is flowing in one direction, we're going to get either a magnetic field oriented up, or if we have current flowing in the opposite direction, we're going to get a magnetic field that has a net direction down. And if we put this microstructure on top of a permanent magnet whose field is always in the up direction, then we can essentially choose whether we want this guy to rotate left or right, up or down, etc., by which coils we energize with a particular direction of current, right? So for example, if I had a magnetic field coming out of this guy that was direction up, and this guy that was direction up, and then this guy that was direction down, and this guy that was direction down, how would this thing rotate? It'd be rotating. So the top would be rotating out of the page, the bottom would be rotating into the page because those top fields are in the same direction, so they are going to oppose each other. The bottom fields from the bottom two coils are in the opposite direction of the applied field, and so they're going to attract each other. And then if I had the ones on the left in line or parallel with the external field, and the ones on the right anti-parallel with the external field, then it would twist to the right and so on and so forth, so that we can get four axes or two axes of rotation out of this guy. So this is one device that was generated utilizing magnetic repulse and attraction to get its actuation. Another one, and I'll just draw this one over here on the left-hand side pretty quickly, would be something like this. So I'm going to start with a simple anchor over here and an anchor over here. Once again, I'm going to have a torsional spring like so, and then I'm going to have effectively a big cantilever beam on both sides like this. I'm going to put a little divot into here, and you'll see the divot when I draw this in a side view here in just a second, where this cantilever was made out of a material called permalloy, and it is magnetic. Okay. We had a coil underneath one of those legs of the cantilever beam. And so we are able to either attract the left-hand leg towards the coil or push it away from the coil, depending on whether we pass a positive current through the coil or a negative current through the coil. So as a side view kind of thing, our structure would look something like this, okay? So here is our permalloy structure. Here's my little divot. And then this permalloy structure would have been deposited on top of some gold or something else that is very conductive, right? So this is our gold layer. The top is a permalloy layer. And then this dashed red line right here is our axis of rotation. Then we might have a substrate. This would be a contact. And then here is our coil, right? So we'll have a couple of wires like so. Just let's say that these are carrying current in this direction. These are carrying current in the opposite direction. And so essentially what's going to happen is it's going to, like I said earlier, it's going to wind up either attracting that left-hand leg down towards the coil or repulsing that left-hand leg away from the coil, essentially holding the switch open or holding the switch closed. So this is a magnetically actuated RF switch. If we put a permanent magnet underneath this substrate, our switch would have memory, meaning that it could latch into a closed position or an open position easily. So the permanent magnet needs to be strong, just strong enough to hold the tip in place, either on the contact or on the coil when you remove the current, so that when you have it the opposite way, it can easily overcome, or when you pass the current in the opposite direction, it can easily overcome that attractive force to cause the switch to actuate in the other direction. So that essentially you don't need to be constantly supplying power to the coil in order to hold the switch closed. All right, so that is magnetic actuation. So we've got 20 minutes left. So you guys have any questions about anything? If not, see you on Monday.